Okay class, we will solve second example on the compression member. This is example number 5.2 from your textbook. I will read out the example for you guys. The example says a single angle strut ISA 50 into 50 into 6 millimeter of a roof truss is 1.06 meter long period. It is connected by one rivet at each end period. Determine the shape load this strut can carry period. So basically this is ISA 50 into 50 into 6 millimeter, and it is used as a strut, that is compression member, and length is given as 1.06 meter long. Nothing is mentioned beyond that, so take this is as effective length. So our effective length L or small l is 1.06 meter. So it is held in a position at both ends, so capital N and L will remain the same. That is about small l or effective length. Then from the steel table find the properties for this ISA, that is angle. So for this ISA, A, that is area of cross section, will be 5.68 centimeter square, 5.68 centimeter square. Then R minimum is equal to R V is equal to 0.96. This is 96.96 centimeter. What is RVV, or which is RVV axis? You can see that in the steel table. So R minimum will be for RVV axis, and that is 0.96 centimeter. So once we have that information, our job is to find lambda max. So we know that it will be small l divided by R minimum. So in this case it is 1.06. Let's convert that into centimeter and then use the value of R minimum in centimeter. 0.96 will be R minimum. So this will give us lambda max equal to 110.42. Once we have the lambda max, our job is to find out permissible compression stress from the table 5.1. So this is again table 5.1, right? So interpolate it for the values between 110 and 120, right? So our value for lambda max is equal to 110.42. It is slightly higher than the 110, but still we need to interpolate. So if we interpolate that, sigma AC will come to 72 minus 72.64 and just 0.42 higher, right, and divided by 10 here. So this value will come to 71.664 megapascal, right? So we are using the values for 110 and 120 in from the table 5.1. so they are respectively for 110 and 120 lambda max. And again, if it is not given about the Fy, this is safe value to assume Fy, that is the yield stress 250. So if it is not specifically mentioned, then this value will be good. So these two values are particularly this value and this value are for 110 and 120 lambda max, and for Fy equal to 250. So our sigma AC comes to 71, I forget here, 0.664 megapascal. But there is one more thing we need to consider of whatever the sigma AC or permissible compression stress we calculated, that is 71.664. This is not final value, because this is a special condition. Strut is held by the rivet, single rivet. So strut, this particular strut or compression member is held by single rivets, right, or nut bolts, doesn't matter, single rivets, one at each end, right. So for this condition, if you see the table 5.3, see the table 5.3, so we have to reduce this value, we need to reduce this value, or we need one more multiplier from table 5.3 or to satisfy the conditions in table 5.3. So our sigma AC will come to, again there will be one more multiplier, that is 0.8, right, 0.8 of actual sigma AC. So this is, we can call it corrected, right, sigma AC corrected. So our 0.8 into 71.664, so this will come to 57.33 megapascal or Newton per millimeter square. So we have the sigma AC and we have the area also. The next job is very easy, that is to find the compressive load, or the force will be again area and trace, right, permissible trace. So but here use corrected value, right, or final value of the sigma AC corrected into again area. I will just write it area, and now put or plug in the values. So it will be sigma AC is 57.33. So to make it kilonewton, divided by 1000, and area is 5.68 into this is in centimeter square, so this area is in centimeter square, so make it in millimeter square. So 100 is the multiplier for that. So finally you will get, I will say, total compressive load carried by this particular compression member. So finally we will get it 32.56 kilonewton. So that's it for this problem. Thanks.